Hello, I'm EHolfmann. I'm at Old Dominion University in Norfolk, Virginia in the U.S. As this contribution to the Western Boundary Current workshop, I'm going to talk about modeling Western Boundary Current interactions, approaches, and challenges. The work I'm going to talk about has been done by the U.S. ECOAST team, where ECOAST is U.S. Eastern Continental Shelf. The U.S. ECOAST team is shown here. The biogeochemical modeling component was led by Marjorie Friedrichs at the Virginia Institute of Marine Science. Physical circulation model was led by John Wilkins' group at Rutgers University, and the land ecosystem modeling is from Han-Chin Tian's group at Auburn University. The significant satellite data analysis component was done by Antonio Menino and Sergio Signorini at NASA Goddard Space Flight Center and Kim Hyde from NOAA. Funding for this project was provided by the NASA Interdisciplinary Science Program. So as a start, I want to give a brief background on how we got to where we are right now, and then I'll go through the development of the model that the U.S. ECOAST team used. All right, so if we go all the way back to 1988, there was a physical biological model published for the South Atlantic Bight, which is the South Atlantic Bight is the area between the tip of Florida here and Cape Hatteras. The black square here is the domain used for the model. There's a blow-up of it shown here to the right. The Gulf Stream runs right along the edge of the continental shelf here. The model that was used at this time was a horizontal plane model, and the reason for that was there was at the time no ability to do a real circulation model for this region. But there was a current meter array that had been deployed on the continental shelf, and so the circulation model, if you will, was done from optimal interpolation of the current meter measurements. The model itself was relatively simple, consisting of just nitrogen, phytoplankton, a copepod, zooplankton, and detritus. All right, so this model I'm going to talk about a little bit later. Just point out here the 75-meter isobath is here, the 40-meter isobath is in here, and I'm going to show you some flux estimates that were made for those two isobaths. But anyway, this was sort of a start. All right, so we fast forward now 30 years, and we now have these beautiful models that include realistic circulation models, as shown here to the right at the top for an example of a model run for the East Australia current. We also have the ability to simulate the three-dimensional structure of the lower trophic levels, which is shown here for the East Australia current as well. We also now can simulate the large-scale connectivity of the western boundary currents, and this is an example done for the Agulhas current here for a simulation that places the results from the western boundary current simulation of the Agulhas in this area here and its connectivity to the larger flow. We can also look at these other examples of models. This is one up here from Roy Ying He's group at North Carolina State University. Again, the South Atlantic Bight here, a large-scale model. And then the bottom picture here is the Kuroshio and Kuroshio extension. And we see in this one the large meandering mesoscale eddy field that is resolved by the models. One of the clear results from all of these models, even going back to the very simple one for the South Atlantic Bight, is that these systems are advection dominated. As a result of that, there are short residence times, and there's also this large-scale connectivity. As a result of the advection dominated system, the export of carbon and nitrogen is quite high. It has seasonal variability, as work done by Dana Savage and Bill Savage at Cape Hatteras is shown, and there's also interannual variability. And one of the things to think about is with these systems, if we want to look at carbon and nitrogen budgets in order to understand the processes that are controlling this export and also the seasonal and interannual variability. And to do that with the nitrogen budgets, they allow us to apportion cause and effect in what is controlling the magnitude of those exports. All right, so if we go back again to the South Atlantic Bight, this is an example of work done by Joji Shizaka. And what he did is he used that simple little model for the South Atlantic Bight to estimate the carbon and nitrogen fluxes across the 75 and 40 meter isobaths. So the panel here on the right-hand side shows the flux across those two isobaths. And you can see that for this time period of the month of April, there's a lot of variability. There's high frequency variability in the nitrogen flux, which is not reflected in the phytoplankton carbon flux. But we do see that the fluxes across the two isobaths are different. So if you look at more of an aggregate picture, which is on the left-hand side here, you can see that there is considerable offshore export at the outer shelf region. There is a significant amount of on-shelf import, if you will, of phytoplankton nitrogen, nutrient nitrogen. And at the bottom, there is, in fact, a net on-shelf flux of nitrogen. So we're able to start building up these pictures of the variability of the system. And also we're getting from this the idea that the mid and outer shelf processes may in fact be decoupled from one another. All right, but if we want to look at this, we look at the biogeochemical processes controlling that variability of the lower trophic levels. And what's shown on the right here are a number of conceptual budgets models, some actual budget models for various shelf systems. Not all of them are western boundary currents, but what it shows is that there are a large number of processes and the magnitudes of which control the carbon and nitrogen fluxes. One of the things we look at these models is that we need to know the inputs. These are the rivers, the estuaries, the atmosphere, the circulation, the sediments. We need to understand the transformations that go on through the biological and biogeochemical processes. We need to understand removal processes through the circulation, burial, deposition, and then understand these at various types of time scales, such as seasonal and annual, and spatial scales that are regional, and understand the continuum that exists from the land to across the shelf to the western boundary current. So how do we do this? All right, well, what I'm going to do now is talk about a model that was put together by the U.S. ECOAST team. And this model is a coupled biogeochemical circulation model, and it has been applied to the Mid-Atlantic Bight region, which is just north of the South Atlantic Bight. All right, so that's what I'm showing here is the Mid-Atlantic Bight. So the South Atlantic Bight, the area I was just talking about, is here. The Mid-Atlantic Bight is this area up here. The Gulf Stream runs along the shelf along the South Atlantic Bight. It separates at Cape Hatteras, but it's still going out across this area in here. So the model structure consists of a circulation model based upon an implementation of the regional ocean modeling system. The details don't matter so much, but it's been nested in the larger North Atlantic HICOM model, which provides the boundary currents and inputs into this smaller model domain that's been set up for the Mid-Atlantic Bight model. Right. So within that model is a biogeochemical model that tracks nitrogen and carbon. And these are these diagrams here are from a paper that was done a while ago by Katja Fennel, but it's been added to significantly since then. The full dissolved organic carbon, dissolved organic nitrogen dynamics have been included. It now includes multiple phytoplankton components, and it tracks the nitrogen and carbon separately. And there are processes that allow exchange with the sediments and the atmosphere. Now, the inshore boundary of this is the estuary and the land. And this comes from the land component comes from a dynamic land ecosystem model that's done by Han-Chen Tian's group at Auburn. And this starts with what goes on in the watersheds of the various estuaries, processes the information or the nitrogen and the carbon, if you will, and then brings that down the rivers and into the estuarine system. So looking at land use, atmospheric changes through the dynamic land ecosystem model, and then the river discharge for freshwater balance and also nutrients. All right, so if we take those various pieces and put together the U.S. ECOS model, we have this type of structure here. The anthropogenic terrestrial forcing, the land cover, fertilizer, sewage, and all that starts here. And from that, we get fluxes of various nutrients, which then go into the land module or model here, where again, there are transformations take place. And then from that, there's a flux of water and various nutrients or constituents there into the estuary. Once in the estuary, these are processed through the biogeochemical and biological processes. There's a flux out of the estuary that then goes to the continental shelf. So this provides the land, estuarine, ocean continuum that provides the inshore boundary condition, if you will, for the continental shelf. And then the outer boundary condition comes from our circulation and the embedding this model into the larger North Atlantic circulation model. All right, so we've got this big model. We've got all these pieces to it. How do you evaluate these things? Well, we have satellite information available to us as well as in situ data. And so how do we do this? All right, so we evaluate using comparisons with different types of satellite products. And I should say all of the other models I talked about at the very beginning here use some form of satellite data for model verification and calibration. So there's several satellite products that are shown here. We use these to give us a quantitative estimate of the model skill and to assess how well the model is doing. The other thing we can do with the satellite data is because we were working with the group at NASA, they actually developed algorithms for apportioning the phytoplankton community based upon the ocean color information. And so we have, as I said at the beginning, we have multiple phytoplankton classes within the model. And so we use these regional algorithms to put that in, to apportion the ocean color derived chlorophyll into these various phytoplankton groups. And then we can use that to assess or estimate how well the model is doing at simulating those groups. So how do we do the actual comparisons? These are done with statistical comparisons using target diagrams, which are shown over here. And you can see that this gives us an estimate of the spatial gradients and the timing, how well they're doing. The spatial gradients are not doing, if you can see these small dots and squares here, the spatial gradients are doing okay. We're not doing that well with the timing of events or various events here. The Taylor diagram gives similar, again, a similar way of estimating the quantitative skill of the model, and we get the same results with that. The model we're using does okay getting large-scale gradients. It's missing on timing of things. So this indicates that there are model processes that need refinement, but it also tells us what types of data we need in order to do a better job of estimating of formulating the model, but also estimating the skill of the model. All right, so the other thing here, as I said at the beginning, we're looking at regional fluxes. All right, so if we want to evaluate nutrient fluxes, I think that that's one of the real challenges we have. All right, so we can simulate primary production. We can get these beautiful looking fields. We can simulate air, sea, CO2 fluxes. Right, those come out of the model as products from our model. But how do we assess whether or not these are even realistic? Well, the data that we have available are things like this, like an annual primary production estimate for the Mid-Atlantic Bight. And if we use that number, which is based on a lot of in situ measurements, and then compare that number to the model, it tells us that the model is underestimating primary production. All right, well, if it's underestimating primary production, then that has implications for what the carbon and nitrogen fluxes are. The other thing is similar if we look at the simulated air CO2 flux. Again, we're using an aggregate value, an in situ aggregate value, to compare to an aggregate value from the model. And in this case, if you look at the simulated air CO2 flux, this shows a lot of spatial structure along the shelf, which is not picked up in these aggregate types of metrics that we have usually to evaluate these models. So we don't know in many ways whether or not what the model has estimated really is an underestimate relative to this in situ estimate, but we also, the same thing can be said here. But these are the types of data we have and probably need to do a better job at evaluating these types of fluxes. All right, so if we go now and actually look at some of the fluxes that were estimated from the model, which are shown here, this is a nitrogen flux, and this is from some work that Marjorie Friedrichs did. Because we can separate out the different parts of the model, this is what's shown on the right panel here are the different components that go into estimating a nitrogen flux. And if we look over here at the aggregate values based upon the simulations, and this is a 5-year simulation, we get these kinds of numbers here, where we can estimate the dissolved inorganic nitrogen and total organic nitrogen flux from atmospheric deposition, what's coming in through the estuaries and the rivers, what's being exported from the shelf at the shelf edge, and what's coming into the shelf from the area north of the shelf. We also can estimate the amount that's buried, the rate, the amount of and the amount of denitrification. All right, so this allows us then to have a budget. And I should also point out here that the net community production, which is the net of all of the biological and biogeochemical processes on the shelf, is also estimated. All right, so this gives us now an idea of what's important and what processes we might want to look at in order to refine this budget. All right, so if we go and look at the 5 years that went into those more aggregate types of estimates, this is the total nitrogen flux now for these 5 years, the inorganic nitrogen flux and the organic nitrogen flux. All right, so if this Ne plus Cs, this is the export from the shelf plus the import onto into the region from the north. All right, so if we look at this, the largest variability in the horizontal fluxes is from these advective fluxes. There is estuaries and river have an important flux as well. Atmospheric deposition and the burial and denitrification processes on the shelf are not as large. This is for the total nitrogen. If we look at inorganic nitrogen, what we're seeing is that the net community production on the shelf is important in regulating this flux, but also the advective flux is very important. And also, if we look at the organic nitrogen, we see a similar pattern. All right, so there's little variability in the burial and denitrification and atmospheric deposition rates, but what we see is that there is a lot of variability in the net community production and in the advective fluxes. So what this does is allow us to apportion the inorganic and organic nitrogen variability. So now if we look at a north-south section along the Mid-Atlantic Bight, which is shown here, and this is the part across the northern part of the model domain. The red numbers are what are in the nitrogen nitrate that's entering the Mid-Atlantic Bight, and the blue is what's leaving the Mid-Atlantic Bight. All right, so if we look at this, there is a large area of export from the Mid-Atlantic Bight around the mid-shelf region, but there's a lot of import to the area from the shelf areas to the north of the Mid-Atlantic Bight. Now, I should point out that this is related to the strength of the Labrador Current, and I'll come back to that at the end here. But we can now, because of the modeling we can now start looking at areas of export and import to this shelf system. One caution here, though, is that the nitrogen fluxes are dependent upon what's in the biogeochemical or leucotropic level dynamics model, and adding more phytoplankton and zooplankton components changes the amount of denitrification and burial on the shelf and changes it by a significant amount. So this is just a caution that that's why we need to be careful about what the processes are and how they're included in the model. All right, so now if we look, what is the export and the fate of this material? All right, so we'll look here at the Mid-Atlantic Bight nitrogen fluxes. The red are fluxes that are inputs, the blue are fluxes that are outputs. All right, so the rivers and the bays, we introduce this amount of teragrams of nitrogen per year as DIN, and we can apportion it into inorganic and organic and particulate components here. All right, the effective flux is the outward flux, and what we can see for the total nitrogen, this is the number here. There is a large input to the shelf from DIN, and there is export of DON and PON. So the river and estuarine DIN is almost half of the advective DIN flux. All right, and so this, so if we can look at this, we can start now looking at how these different fluxes add up to give us the nitrogen and carbon budgets for the continental shelf. But then what we might ask, we've got all this DIN coming in. What is the fate of that? All right, so then we start looking at a larger scale system here. So the East Coast has all these rivers. So there are 21 rivers. So what do we do with this? So what we do is we put tracers at the mouth of all these rivers and ran it for a 5-year simulation to see what happened. All right, so this is for the Mid-Atlantic Bight part only, but there are lots of different fates. But the one I'll point to that's relevant here is a lot of this material coming out onto the shelf is actually picked up and entrained in the Gulf Stream. There is a significant export from the shelf to the Gulf Stream, which then gets picked up and carried out across the North Atlantic. There are other areas of transport to the north and to the south. So there is connectivity between the Mid-Atlantic Bight and the South Atlantic Bight. And if I had showed you these simulations here, you'd see that this gets picked up and moved off the shelf as well. All right, so now there is interannual variability, and that's all I want to show with this slide is that we can see from these 5 years of simulation that the amount of variability is considerable, but there is still here at Cape Hatteras and even along the Mid-Atlantic Bight, there is this export in the Gulf Stream of these materials. All right, and so there is an effect of the river estuarine export onto the shelf. And one of the things to think about is how does this vary with things like climate and land use? And that's the next piece I want to talk about here is the climate and land use changes, because this is what would underlie projections of how this system is going to change over the next decades. This is an area that has not been really looked at. I'm not sure that we as a community have the information or the background for these areas to allow us to really look at climate projections and what's going to happen to these regions over, in 2050 and 2100. So some summary remarks is that we know how to estimate the annual and interannual shelf nitrogen and carbon fluxes and variability. We know that we need to do this. We need modeling, remote sensing, in situ data analysis, and process representation. I think we know this one fairly well, at least what we need to do. From that, we can develop nitrogen and carbon budgets that allow us to identify processes, sources, and sinks, and to attribute cause and effect. The nitrogen budget analysis for the U.S. continental shelf shows us that, again, it's an adductively dominated system, at least for the inorganic nitrogen across the ocean boundaries, and the biogeochemical and biological processes on the shelf moderate the magnitude of those fluxes. All right, so where do we want to go with our state of understanding here? I think we're pretty good at doing the circulation to plankton types of models. They can be made better by improving process representation, by improving the resolution of the models, but I think that's something that we as a community really know how to do. We know how to assess the uncertainty of our models, but to do this, we need a suite of measurements. Right now, we're mostly using satellite information, but the in situ data to allow us to do the skill assessment for these models, I think is not there, at least not at the level that we need it. And that might be improved through the things of gliders, AUVs, and those kinds of things, but those types of instrumentation platforms, but we need to learn how to use that kind of data to assess the skill of the models. Developing projections for these systems, I don't think that's been done. I think that's something that is a challenge and something that perhaps we can discuss as part of our workshop discussions. So I'll stop at that point and say thank you, and I hope that this discussion will be continued when we meet as a group for the Western Boundary Current portion of the workshop. Thank you very much.